Question 2 continued part D. The technician now sets up a linear air track to demonstrate the Doppler effect. The vehicle is fitted with a buzzer, a microphone is connected to a computer, and the vehicle is held stationary and the buzzer is switched on. The buzzer emits sound with a frequency 845 Hz, and for 3 marks it says the vehicle now travels at a constant speed towards the computer, or the microphone, and the frequency of sound measured by the computer is 849 Hz. And we've got to calculate the speed of the vehicle along the linear air track. Well, we go to our relationship sheet and we know that the observed frequency in the Doppler effect is going to equal to the frequency of the source, and it's going to be multiplied by the bracket of speed of sound divided by speed of sound, and it's plus or minus the speed of the source. Now we've got to find that speed of the source here, but we've also got to ascertain first of all which we're going to use plus or minus on the denominator. And the rule of thumb is quite simple. If the object is approaching you, which is creating the sound, you think of the distance getting less, therefore you're going to use the minus sign. So therefore our equation we're looking for is F naught is equal to Fs, the frequency of the source, V divided by V minus Vs. And that's our working equation. Now we have to find Vs out of that, and you know, if we put the numbers in, it could be quite easy doing numbers, but it can be a wee bit frankly as well, because we've got the speed of sound to get rid of all here as well. So I would suggest that we should have rehearsed this to the fact that we can change that to the subject Vs. It's a higher maths problem when you think about it. So first of all, here's how we did it. We do frequency observed sound, we divide each side by Fs, and that's going to give us V over V minus the speed of the source. Remember, V is the speed of sound. Now a little trick here to get Vs up on the top, to make it easier for manipulation, we just do Fs, we swap the fraction round, Fs divided by F naught is going to equal to V minus Vs over V. And then we can multiply both sides by V, I'll do this over here, and we get V Fs over F naught, frequency of the source, over F naught, and we're going to get that times V, and it's going to be equal to, in this case, V minus Vs. So if we add Vs to both sides, we're going to get Vs plus V Fs over F naught, and that's going to leave us this side with a V. And we can see now we can take away the V Fs F naught from this side to the other side, and we end up with the speed of the source is equal to speed of sound, take away speed of sound times Fs over F naught. And that's just got the expression we can plug numbers into now. We don't need to go any further in that aspect, we can just plug in our numbers. But to be a wee bit more mathematical, we could say we could take out a common factor of V, the speed of sound, and we have 1 minus Fs over F naught. And that's a good relationship to sort of kind of like have under your sort of kind of like your weapons to do this type of equation, because it's a quite simple equation to find the speed of any object moving towards you that's emitting a sound of frequency F naught, Fs, and you know F naught. You can just plug these things into the equation. So what is the speed of the object moving towards it? It's the speed of sound, 340, times 1 minus the frequency of the source, which we found out was 845, it tells you that, and divided by what you observed, which was 849. And we do that in a bracket. Simple case, working your brackets, and we end up with the speed of the source is 1.60 meters per second. That's well within the normality of that type of experiment. It's kind of a long thing, but be prepared. Made sure that you have the rehearsal to change that subject to the formula. Vs giving you that expression. Question 2D continued part 2. Explain in terms of wavefronts why the frequency of the sound detected by the microphone is greater than the frequency of sound emitted by the buzzer. You wish to use a diagram. Well, we can go back to our basic diagram for the Doppler effect with a car, and if we look at this situation here, you can see the diagram explains why. In this part of the diagram here, imagine the car to be the buzzer. If it's not moving, all these sound waves radiate out like that with a constant wavelength. So this person here would hear the same frequency, count the same number of waves, as that girl here would count the same number of waves. Therefore, that person would hear the same frequency as this person here. But as the car moves towards the person, it catches up with the wave fronts, and the wave fronts ahead of it will be crushed up, which means this person here, aka the computer's microphone, will detect a higher frequency in this side as it was when the buzzer was not moving. So it's all to do with the wave fronts crushing up, because the source of sound is actually going forward and catching up with the waves. Now that diagram there will give you the marks for that. The wave fronts at the front, as it approaches this person here, this could be the microphone, are all crushed up. Question 2, D continued, part 3. It says here, a student standing at the end of the linear track near the microphone states that they did not hear the small change in frequency. For 1 mark, using the same apparatus, describe how the Doppler effect could be made more obvious for the students. Well, we go back to the equation, the observed sound for the Doppler effect. F naught, the observed sound, is the sound of the frequency of the source, and it's going to be into the speed of sound, and divided by the speed of sound, and because it's approaching the microphone, it'll be minus Vs, where Vs is going to be the speed of the source moving towards you. Now, in order to make the observed frequency bigger, so as you can actually hear a detectable change, you'd have to make Vs a lot faster. So if you increase Vs, you're going to have a speed of sound take away an increased value, which is going to give you a lower number on the denominator. And if you divide by a lower number, you'll get a higher frequency of observation. So to make it stand out more, you would actually have to increase the speed of the source. In other words, in this case, you'd have to make that little cart go faster. So you have to increase the speed of the source. And that backs up the equation. If you increase Vs, you're going to get a smaller number, because speed of sound take away a bigger number. It's going to give you a lower number than before, and the numerator divided by a smaller denominator is going to give you a bigger F naught, and that means you'll be able to hear the frequency a bit better.